Hi students, let's continue our discussion of electrostatics. In this part we are going to see the electric lines of forces, equipotential surfaces, etc. Now there were three ways to represent the electric field strength. One is the electric field intensity, second electric potential, and third one electric lines of forces. Now what is this electric lines of force? That's what we are going to see here. Actually, the name itself is telling that these are some lines. Electric lines of forces means these are some lines which are representing the electric field. So we can say it is a graphical way to represent the electric field. And in an electric field region, we draw some lines. These lines are not actually there. They're imaginary lines, but we'll draw some lines to represent that this is the field here. These lines will tell us that what is the magnitude and what can be the direction of the electric field there. So in formal language, electric field is represented by some imaginary lines in such a way that tangent drawn to these lines, you see here, some lines have been drawn like this. So if you draw the tangent to these lines, like this here, like this, then this tangent will give you the direction of the electric field. And how many field lines are crossing? You draw one area of 1 centimeter square, then how many lines are crossing? That number of field lines crossing unit normal area gives you the idea about the magnitude of the electric field. Let's read the statement. Electric field is represented by some imaginary lines in such a way that tangent drawn to these lines gives the direction of electric field, and number of field lines per unit normal area. Normal area means if this is the area, normal to it, how many lines are crossing, right? So that gives you the magnitude of the electric field. More is the number of field lines crossing unit area, more will be the field. So if you see here, I have drawn two areas A and B, surface areas, which are equal in magnitude. This particular area is going to be equal. Now, if you see at point A, 4 lines are crossing this, and at B only 2 lines are crossing. So more number of lines are crossing the unit area at point A than at B. So we can say electric field intensity is going to be greater at A than at B. This is what about. Now, due to some basic charges, some field lines we have drawn, you see that. Or before that, see some basic factual points about the electric field lines. These are the imaginary lines. In actual, no such real lines exist like that. This is purely our imagination, that in this electric field region, there are lines like this. But in actual, there is no lines, but it is only a way to analyze the electric field in that particular region. And if it is imaginary lines, then you can say one person from 1 coulomb charge can draw 10 lines, other person can draw 200 lines also. Yes, absolutely right. You can draw any number of lines. We can draw any number of field lines from a given charge. But you have to remember one thing. Say for example, you are making this line diagram for 2 charges. This is 2 microcoulomb and this is half microcoulomb. Then if you are making 8 lines from here, say 1, 2, 3, 4 and 4, 8 lines from 2 microcoulomb, then from half microcoulomb you have to draw only 2 lines. Means you can draw any number of lines, but the number of lines must be proportional to the charge. You draw 16 lines from here, then from here you have to draw 4 lines. If you draw 200 lines from here, then for 2 microcoulomb 200, then for half microcoulomb you have to draw the 50 lines. the number of field lines must be relative, that must be proportional to the magnitude of the charge. This is a very important point. You remember this point, right? Electric lines of forces cannot intersect each other. Try to understand this. If two electric lines of forces will intersect, then at the point of intersection, at this point, this line, line 1, will give you the direction of electric field this way. Say I am marking it as 1. And line 2 will give you the direction of electric field this way, 2. Is it possible that at the same point there are two directions of electric field? Not possible. That's why, remember, two electric lines of forces can never intersect each other. Electric lines of force start from a positive charge and terminates on the negative charge. You see these two diagrams. This is positive charge and this is negative charge. Electric lines of force will start from this positive charge and terminates on the coming arrow's direction. You see arrow's direction. It is positive charge. Field is like this, going upward, outward. Negative charge coming inward. Starts from positive charge, terminates on the negative charge. Electric lines of forces can never form the closed loops. Here I would like to write one note, valid for electrostatic field lines. Why I am writing this? Because in EMI we have another type of field lines also. They can be closed loop. But in electrostatics, electric lines of forces can never form the closed loop. They can never be closed loop. Now another thing you see, say if we have the electric lines of forces like this. Now it means direction of electric field here is in this way. At this point is this way. At this point is this way. If you release one charge particle here, say positive charge particle, then it experiences the force in this direction equal to QE. Now, since force is along the tangent to the field, charge particle will start moving in this direction. When it reaches here, the direction of electric field is not along this way or along this way. It will be some other way. So this charge particle cannot follow this curved path. Electric charge particle, when released in the electric field region, is not going to follow the path of the electric field lines, because electric force is only along the tangential direction. But if electric lines of force is a curved path, then we need one centripetal acceleration. Who will provide that force? So remember this point, a very nice conceptual statement. When a charged particle is released in an electric field region, then it is not necessary that it will follow the path of field lines. It may follow if the field is uniform. If the field is uniform, then it will follow the path of the field line. But if the field is non-uniform, it is not going to follow the path of field lines. In electrostatics, electric lines of forces cannot cross the conductor. What it means, that also I would like to explain. Let us say this is conductor, and say here is this is the conductor, this one. Here it is hollow conductor I am taking. Here some air enclosed, here also some air. Then in electrostatics, electric lines of forces cannot cross here. They will be from any inside point only to the inner surface, or from the outer surface to the outside path, or it can be from some outside point to the outside surface and inside surface to some inner point. In this region where the bulk of conducting medium will be there, electric field lines won't be there. Why? Because in the electrostatics, electric field intensity in the bulk of conducting medium is 0. This is also a very nice statement. So it is a very little topic, very small topic, electric lines of forces. These are the imaginary lines. The tangent drawn to them gives the direction of electric field. Relative number of field lines crossing unit normal area gives you the direction of the magnitude of the field. The number of field lines drawn from any charge must be proportional to that charge. You can draw any number, but if you are taking 2 charges, then from 1 charge, if you are taking 10 lines, then from 1 coulomb charge, then 2 coulomb charge, you must have to take 20 lines. The lines, electric lines of forces start from the positive charge, terminates on the negative charge. They will never form the closed curves in the electrostatics. Now let's take the next topic, next small topic, equipotential surface. What is the meaning of the word equipotential surface? Equipotential surface, any surface where at every point of which potential is same, that is the equipotential surface. Let us say this is the surface and at every point potential is same. At every point of this surface potential is same, then it is said to be equipotential surface. At every point of which potential is same, that surface is termed as the equipotential surface, right? Electric field intensity at the boundary of the equipotential surface is along the normal. Let's try to understand this point. If you have this equipotential surface, if this is an equipotential surface, then that point is telling electric field at this point, at any point on the surface of equipotential surface, must be along the normal, means in this direction. Electric field cannot be in this direction. This is the normal and this is not normal. So they are saying electric field in this direction is not possible. Let us say it is in this direction. Then we'll prove it is possible or not. Right? So let us assume it is in this direction. Then this electric field I can resolve in 2 components. Say this is theta, one the E cos theta, one E sin theta. One component along the surface and one component along the normal to the surface. If electric field is there along the surface, the charged particle at the surface are experiencing the force and they are allowed to move along the surface. And if the charged particle is moving, then it is not a condition of electrostatics. In electrostatics, charge cannot move. So if electric field is in this direction and it is having some component, it cannot be in electrostatic equilibrium. To attain the electrostatic equilibrium, field has to be in this direction. So a very nice point. Electric field must be along the normal to an equipotential surface. Electric field at the boundary of an equipotential surface is along the normal. Right? Now another point you see, 2 equipotential surfaces cannot intersect each other. Why? Now if they are intersecting, this surface 1 is telling the field at this point is in this direction, 1. And this second surface will say the field at this point is in this direction 2. Now if they are intersecting, the field at one point, same point, will be in 2 directions, which is not possible. So it means 2 equipotential surfaces cannot intersect each other. This one. Now, work done by electric force in moving the charge from one point over other on the equipotential surface is 0. This is also very nice statement. They are saying if electric force is there, work done by the electric force in moving the charged particle from one particle to point to other on the equipotential surface is 0. Since here we'll see this way, electric field is along the normal. So the component of the electric field along the surface is 0. So if the charge particle is moving along the surface, the electric force itself is 0. So what will be the work done by the electric force on moving the charge particle from 1 to 2? 0. It can also be told in terms of the potential. Work done by the electric force is equal to minus of Q V2 minus V1, or V1 minus V2, whatever it is there. Now, when the equipotential surface, these two are same, this will come 0, potential difference becomes 0, then work done by the electric force is also 0. So work done by the charge particle, electric force in moving a charge particle from one point to other over an equipotential surface is 0. Now another point which will help you to solve some question. Any surface drawn in such a way that E is along the normal to this surface is an equipotential surface. You draw any surface by keeping one point in mind, that electric field intensity to this surface is along the normal at all the points. Then this surface what you have drawn will become the equipotential surface. Let's see the equipotential surfaces because of some charge distribution. Let us consider one point charge is there at the center. We have drawn three spherical surfaces whose center, concentric spherical surfaces, the center of whose is coinciding with the location of charge. Then if you see here, electric field will be along the normal, this way. So if electric field is along the normal, potential at this point, same. Potential at this point, same. Potential at these points, same. So we can say 1 is an equipotential surface, 2 is an equipotential surface, 3 is an equipotential surface. If you are able to draw the equipotential surface, then determining the electric field intensity with the help of the Gauss law will become a very easy task. Now let us say this is second case you take, it is infinite line charge. Now infinite line charge, if you remember, due to infinite line charge, the electric field intensity at any distance is lambda upon 2 pi epsilon naught r. So whether you take the point here, but if it is at the same distance, field is same. So we can say due to infinite line charge at the same distance from the wire, field is this way. So if we draw a cylindrical surface with the infinite line charge as its axis, then this surface, I am telling you, this surface, this one, this cylindrical surface will become an equipotential surface. If you have the uniform electric field throughout the space, then you draw one surface like drawn perpendicular to the field lines this way, then this surface will be an equipotential surface, like the third diagram you see we have drawn. So equipotential surface is also a very important concept. Once you know that what is the equipotential surface, you can answer certain questions very easily, right? Next topic will take the electric flux. It is also a very small topic. You remember these three parts: electric lines of forces, equipotential surfaces, electric flux. They are very much required to understand the Gauss law in effective as well as behavior of conductors in electrostatic. Also you can understand it well by using these concepts. Now electric flux, it is defined as the dot product of electric field with the area vector. Now like say for example, see on the screen, this is a one surface small surface element, I am taking ds vector, small surface element. And in this region, some electric field is present. And these are the electric lines of forces which are crossing like this. Then we define an area vector which is perpendicular to the surface, which is perpendicular to the surface. If I take this as the surface, then this will be the area vector along the normal to the surface. So here, if this is the surface, this is going to be the normal area vector. So area vector is a vector whose magnitude is same as the area of the surface and whose direction is along the normal to the surface. If this electric field is making an angle theta with the area vector, then flux linked with this surface will be given by E dot ds, E ds cos theta. This flux can be positive, negative or zero depending upon theta is acute, obtuse or right angle. Now, what is the physical significance of this? Say, you can say physically the flux can be interpreted as the number of field lines crossing the unit normal area, crossing the given surface. Say for example, if I have one surface, this one, and if I take the similar type of surface, this is little smaller, it becomes this one. And if I'm having the field lines like this, then you see this field line is crossing this surface but not crossing this surface, crossing the straight surface but inclined surface it is not crossing. It means the flux linked with this surface, left surface, is more than the flux linked with the right surface, even though both are of same area. Understood my point? So that's why this unit normal area is going to make the difference. If you change the angle of this surface like, say this way, then further some less number of field lines will cross through this surface. So number of field lines linked with the surface is the physical interpretation of the flux, you can say. Physically, flux can be interpreted as the number of field lines crossing the given area. Like if I say one example, electric field is there in uniform electric field, you say it is in this direction. Say, and if I take the surface this way, I hope you understood. I am taking this way. Now it is like field lines are like this and surface is in this way. So here no field line is crossing. Here field lines are not crossing the surface, because crossing the surface means like this. So here the field lines is 0. If I change the orientation of this surface like this, then some of the field lines are crossing. So it depends upon the orientation of the surface also, right? So let's take another example, because it is a very important point here. We have some point charge Q and we have one hemispherical surface with open base. There is no base, no lid, only like this. Here no surface, only like this. Now here these 3 lines entering into the surface, but they are not leaving. So flux linked with this surface is going to be non-zero. Now right side, if you see, there we have taken the closed surface, closed spherical surface. Due to this point charge, field lines enter here. I am showing here, you see, this red lines, field lines are entering. How many field lines enter? 4, and 4 left. 4 left. That's why the net field lines entering or leaving the surface becomes 0, and the flux linked with this surface, spherical surface, due to this charge, point charge which is placed outside, will become 0. So flux is a very important thing to understand in terms of the electric lines of forces. Let's take some more example here. Say you have one electric field in this direction, say towards the x-axis, and you have the square surface of 1 centimeter square, and it is placed in the like this way, normal to the electric field. Area vector is along to the electric field. Then what is the flux linked with this surface? Electric field and area vector are parallel. So the flux is equal to E into A into cos 0. Cos A is given, E is given, you can find. But if say for example, you have to find the flux linked with this cylinder, and that too electric field is given as in this direction, E is given, and say this radius is R and length is L. Now if I take the left side part, try to understand this situation. You assume this is coinciding here, and this is here. Now if I take the surface like this, cut it like this, then on this particular part, electric lines of forces are entering, and from this part, right part, electric lines of forces are leaving. Whatever number of field lines entered, same number of field lines leaving. So the net flux will become 0, right? Say another one more you take. If a point charge is placed at the center of a sphere, say this is the center of the sphere, what is the flux linked with this surface, with the sphere of radius R? Then if you see here, electric field intensity at any point on the surface of the sphere will have the same magnitude. Due to this particular sphere charge, electric field at all the points will be having the same magnitude. That electric field will be kq upon r square. Now this electric field is in the radially outward direction, and this area is also along the radial outward normal, means electric field and area vector are parallel. So the flux linked with any small element, if I take a small element of area ds, then the flux linked with this will be E dot ds, and angle between these two is 0. So it becomes E ds cos 0. E becomes kq upon r square into ds. Now when we integrate this small areas integration will give us the total 4 pi r square kq upon r square into 4 pi r square, and we'll get it as q upon epsilon naught, right? So how to determine the flux, it is going to be an important concept, and it is representing physically the electric lines of forces. That is another important point you have to remember. Okay, that's all for now. In the next video we'll continue our discussion with the Gauss law.